In this topic, we'll look at the very powerful Java collection classes, which are so named because they all implement the collection interface in java.util. Now, these provide data structures that are collections of other objects, like linked lists, for instance, or hash tables, or binary trees, and so forth. The collection classes are also a good example of object-oriented design, and we'll discuss several object-oriented design concepts that they illustrate. And this includes 4 new design patterns: composite, prototype, adapter, and proxy. Now, to illustrate the collection classes, we will use a simple parts list and inventory system that I call assemblies. Now, the assemblies, open that up a bit here. The assemblies come in progressively more sophisticated versions from V1 to V2 to V3. And so we'll start obviously with V1. And their source is included as lecture material. And by the time we reach assemblies V3, we'll have about a 400-line application illustrating most of the collection classes of any importance, at least, and also the above-mentioned design patterns. Now, starting with assemblies V1 then, this version tracks a catalog of components, for which we'll have inventories in later versions, though in this version we'll just read in the component data. Now, a component can be either a simple part, like our bolt up here, or a more complex assembly of 2 or more parts, or 2 or more other components, other assemblies. Importantly then, assemblies may include smaller sub-assemblies. As an example, you might consider a computer, for instance, which could comprise a motherboard and a disk and I/O cards, and then a motherboard in turn may comprise a CPU and memory. A disk comprises a controller card and the physical platters, and so forth. Any complex system is hierarchical, with large assemblies comprising smaller ones, and the smaller assemblies comprising smaller ones still, until we get down to individual parts. Now, assemblies V1 reads a description of components from the catalog.txt file that we're looking at right here. And it's also in the transcript, of course. Now, each line describes one component, starting with its name, like bolt, for instance, or nut, or gadget. And simple parts like bolt have just a floating point weight after the name. But assemblies, like gadget for instance, have a list of their constituent subassemblies or parts after the name. If a given part or subassembly appears multiple times in a larger assembly, it's simply repeated in the list. So for example, the file here says that a what's-it component there comprises 2 bolts, 2 nuts, and a flange. Now that's a list of simple parts, but a more complex assembly may comprise other assemblies, as we said. So a what's-it gadget, for instance, which is evidently a gadget bolted to a what's-it, comprises a gadget, a nut, a bolt, and a what's-it. Now, as a quick example run will show here, the assemblies V1 reads catalog.txt and then reports the weight of each component. That's not necessarily in the same order as the file, by the way, and that's for reasons we'll discuss. For a simple part, the weight is as given in the catalog file directly. But for an assembly, the weight is the sum of the weights of the components in the overall assembly. Now, question 1, explain how we got a weight of 1.477 for a gadget by developing a complete parts list for it. Now, this isn't just a legwork job. The point is to get familiar with the hierarchical nature of the weight computation to prepare for the code that we'll discuss in a little bit. So we've had a bit to think about that. The answer is that expanding it all the way out, a gadget ultimately comprises one bracket, 4 flanges, 7 bolts, and 7 nuts. And you have to expand out the whatsits to their individual pieces in order to get that full list. Now that totals to 1.477, and it's easy to compute that because each part's weight, as you may have noticed, is a different decimal position, which makes it easy to total them up. Okay, and then how do we represent a hierarchical structure like our assemblies in an object-oriented design? We use a design pattern called composite. The interface component, to look at here, and its subclasses, assembly and part, illustrate the general approach. So let's start with the interface component here. Now, this has methods appropriate to either a part or an assembly. In an assembly's V1, the only common behavior of parts in assemblies is that each has a name and a weight. So component has methods getName and getWeight. Then we implement the common interface with 2 classes. And the first one is part. And this is for simple elements. There's not much to this class. It just has a name and a weight, as you can see here. And it implements the component methods by returning those 2 values. The assembly class, however, is a little more interesting. Now it has name and then pieces. And the latter is a list of components comprising the assembly. For instance, a 4-element, a list of bracket, bolt, nut, and whatsit if the assembly represents a whatsit gadget. Assembly's getName is like parts, just returns the name, but getWeight is more sophisticated. It walks the list of the subcomponents and totals up their weights and then returns that weight. And so another question here, why did we make pieces a list of component? Wouldn't a list of parts be simpler? And if you thought about that for a little bit, well, the answer is, yeah, sure, a list of parts would be simpler, but it would also mean that an assembly could only contain simple parts, not other subassemblies. Making it a list of component allows the list to contain a number of, or a mixture, I should say, of parts and assemblies, kind of mingled together. Now, these 3 classes illustrate the essential elements of a composite design pattern. The first element is we have a single interface, like component, that lets simple and compound components, parts and assemblies, be treated in common. And it has methods for their common behavior. And the second element is 1 or possibly more classes implementing the interface and representing simple leaf components, like our part class. A more complex composite design than ours might have several different such classes, for different kinds of parts, for instance, if their behavior were different. And then the third essential element is a class like assembly, and it implements the interface and represents a compound component, generally containing a list or other collection of subcomponents. And those subcomponents may be simple or compound. They may be parts or assemblies. This compound class implements at least some of its methods by recursively calling the methods of the subcomponents, like, for instance, getWeight does in assembly. In combination, these 3 elements let you set up an arbitrarily deep tree of objects, with interior nodes of the tree represented by objects of the compound class, by assemblies, and with the leaves represented by the simple classes, part, for instance. And because hierarchical structures are so common in practice, composite is one of the most important and widely applicable design patterns. Some other examples of potential composite patterns might be a directory and file structure with an interface that we might call directory or file, having methods getName, getDiskSpace, and so forth. And then you'd have a class file representing a single file and returning its name and disk space, and a class directory that contains a list of directories or files. And its get disk space might work by adding the child directory or files disk space values to arrive at a total get disk space result. Another example might be a graphical layout structure with an interface that we would call diagram and have a method draw. And then we'd have classes for simple elements like circle or rectangle, and they'd have draw methods that draw the relevant shape. And then we'd have a class compound diagram that had a list of diagrams, which would be simple shapes or smaller compound diagrams. And it would implement draw by calling draw on each child diagram. Now, question 3 is a little open-ended. I'd like you to come up with at least one example of a composite pattern application, following the examples that I just gave. And be sure yours has the same basic elements as the examples given. And if you want a way of evaluating that after you've had a chance to do it, there's really no right answer, but grade yourself on whether you had the following pieces. First, a general interface that represented both compound and simple entities in the design. Then second, several reasonable methods for that interface. And third, at least one simple class implementing the interface. Fourth, a class implementing the interface and representing a compound entity. And then a method of that compound class that did its job by calling that same method on the child entities. In the next segment, we'll look at the UML representation of composite, and we'll introduce new UML notation to go with it.